Okay. Number 6 is 0. Number 14 is E, because you can just use exponent rules, right? E to the x times e to the 1, and then that reduces e is left.
Wait.
Number.
I thought the directions asked to prove that e to the x was smaller.
No. Same.
Never mind, that is what it asked. Never mind.
Okay. Number 18. Number 18, top wins, infinity. Long story short, the e to the x's can just cancel. And since it's an infinite limit, then we know the top grows more quickly. Number 26, limit is infinity again, so therefore the numerator grows more quickly. Once again, L'Hopital's probably would have been the easiest way, I would think, of doing that one. We'll come back to 29 in a second so we can talk about it. Number 32, for comparing two functions. I don't even think, did they say you had to do f2 over f1? You could have done it either way, I believe.
No, but you would have to, prove it in that. It's like f of 1 to f2, like 2 to 3, then 1 to 2. Or if it's like flipped.
Oh, you had 3. I didn't keep looking at it.
Yeah.
Okay, I see. You would have to have the right correlation.
I could put it
Yeah.
They went ahead and did it, and it was kind of, I think, what I showed whoever, I wasn't in there. Who was in here?
I wasn't here Friday.
Someone was showing the multiply by 1 over the highest degree. That wasn't intense. You could have multiplied top and bottom by 1 over x squared, and this one it would have been 1 over x to the 4th. Then you would have gotten to the simplified version underneath the radical, and that could have been 1. That's probably the easiest way. You guys might have done it a few different ways, but I probably would have. In essence, it's your degree test, that's true, but we're showing y, and so you would have multiplied by 1 over the square root of x to the 4th. And then, since that one's a constant and that one's a constant, then we can go ahead and make that correlation. So, since f1 grows the same as f2, f2 grows the same as f3. Well, they did f1 to f3, that works. Then f2 and f3 also work. You could have shown all 3, but you only needed to show 2. Carolyn?
What did you multiply the numerator by?
Oh, it was the algebraic way of doing the degree test back in the day. And you could have, it would have been an in-between step. You could have multiplied top and bottom by the square root of x to the 4th, and so you would have gotten a little like 1 over x to the 4th inside the square root on top, and on the bottom, the square root of x to the 4th would have ultimately just been x squared over x squared. And so, what you're multiplying by is ultimately 1 over x squared top and bottom. So then that one just ends up reducing and being 1. This one, I make the x squared a square root of x to the 4th to bring it in. And that's how you end up with that 1 plus 1 over x cubed.
Because you take out.
Just take out a what? Are you thinking about the absolute value? Is that what's going on? But it's kind of irrelevant because of the x squared and you have a positive square root. Then you take the limit of that expression, and that's what brings you back to. Well, you don't have to take a derivative. You don't have to do L'Hopital's.
I was talking about an earlier one.
Which earlier one? This square root one up there?
This one. 26.
Explain 43.
Like, I didn't know
We actually haven't gotten to the 40s yet. Corey, give me a second. Number 26, if you plug in, ln goes to infinity. Square root of x goes to infinity. So it's really just infinity over infinity, which allows us to do L'Hopital's.
Okay, yeah.
So then L'Hopital's derivative of this one would be 1 over 2 root x, derivative ln 1 over x, and then we just want to simplify our complex fraction. So ultimately that guy goes down, that guy goes up. Then you can just reduce the exponents. Because you have x to the 1 and x to the 1/2, which will end up being just x to the 1/2. And then that's just going to be infinite since it's not wins.
When you say plug in infinity, you're talking about like looking at the graph, right?
Looking at the graph or approaching infinity. So in my mind, I'm, like for these two, I was picturing the graph and I was going to the right. For this down here, I was literally just thinking of, hey, ever-increasing numbers square rooted, that's just going to get bigger and bigger as a quantity. But you're right, you can think about the graph too. Corey?
Does it matter which function's on top and which function's on the bottom?
Technically no, because if you were to flip them, you would still solve, but it shouldn't have been infinity then. it would have been 0.
Yes.
Because then you would be able to say, if you flip them and then the limit was 0, then you could say that the square root still grows more quickly. So conclusion the same, work would be a little different. As we go to number 48 and 50, E and then C.
Yes.
I already heard a question on 43.
43.
I want to talk about 29 really quickly first, since that's where we started. Those are 2 odds I want to peek at real fast. But is there anything else, evens or odds that we want to talk about? Discuss, ask questions. As we're looking, let's peek at 29. Did you find one, Alan?
Let's do 6.
Number 6? Okay.
Yeah.
So number 29, question. How'd you guys think through it and how'd you show it?
You compare.
Alright, what'd you compare first? Did you just go like first,
First
second,
and
third?
last.
Yeah.
The x overall. I don't know.
I would compare the e to the x with the e to the x over 2.
Fastest.
Alright guys, a little bit too much, make it whispering and I'll be okay, alright? So if we did compare, we can call this one like 1 and 2 if you want.
Yeah.
Of e to the x over, how could I rewrite that one to make it a little easier, just in case some people,
E to the 1/2 x.
e to the 1/2 x?
E.
That works.
E to the 1/2 times e to the.
You could also do
x.
that.
Yeah.
So I guess if you did e to the 1/2 x, we guys are thinking of exponent rules?
Yeah, well,
Okay.
we can also do e to the x minus e to the 1/2. E to 2 whatever.
Right.
I mean, how do you-
So I do the limit as x goes to infinity of e to the 1/2 x. 1x minus 1/2 x. When you're dividing, you subtract the exponents. So then that's going to be infinity, right? So who's stronger between 1 and 2?
The
E to
top
the-
easiest one is stronger.
Okay. So far I know that 1 is greater than 2. What'd you compare next?
3 to 1.
3-1. Did you compare 2 to 3?
So how do wait? I'm confused.
I would have done probably 2 to 3.
Because then, yeah.
Because then 1 to 3 would automatically be.
And then you'd have to test 2 to 3 anyways, because you don't know which faster is 2 to 3.
You would have to compare 1 to 3 or 2 to 3 anyways.
No, not if you already know 2. Not if you find 3 is slower than 2, because then you know that 2 is
Right, but
slower
no
than
one's saying you could do 1 to 3 or 2 to 3. Technically could do either one.
But if you do 1 to 3, don't you still have to compare 2 to 3 later? Because you don't know which one's faster between the 2 of them. But if you do 2 to 3, then you know that if 3 is slower or faster, you don't have to compare the other ones, because 1 and 2 is going to be there.
No.
No, it's true.
Think about it this way. If you do 1 to 3, then you can take out the power of x to the outside of the ln of x over e, then top ones anyways, because e is constant.
So Noah's thinking that comparing 1 to 3 is going to be easy, but what Corey's saying is if I know that 1 is greater than 3, then I'm still not going to know about 2 and 3. If 1 is less than 3, then I can go ahead and say, oh, okay, so therefore 3 would also be greater than 2. So it depends on the conclusion basically as to what you can say. So since it is easy to do 1 to 3, first of all, Noah, when you did compare 1 to 3, which one was greater?
Ln of x.
Okay, so since 1 to 3, 3 ends up being greater, then we can say, well, if it's greater than 1, it's also greater than 2. But you're right, Corey, if it was less, then we wouldn't have known about 2 and 3. Kyle, you also had an idea about it.
I just have a question there.
Okay. So go ahead and ask your question. I'm just going to show the 1 to 3.
So what make you, what causes step between, so e to x over e and half x? How do you simplify them be e?
Like bases, we can subtract powers. So if we had, for instance,
Oh, so like same variables?
like bases. So since e is in the base and e is in the base, then we can go and subtract the exponents. Like x squared over x to the 5th, we can subtract the exponents.
Okay.
Or 2 to the x over 2 to the 3x.
And infinity because the top one is greater than e to the x. So that's why you say the first one.
It's a square root of e to the x, and so you can think of the square root of ever bigger numbers.
Well, I'm just saying that, because you said, okay, so limit is infinity. So would that correspond with the top one of the original one? So e to x is stronger than the half.
Since when I compare 1 to 2, the limit is infinity, then the top must be stronger. So then when I compare 1 and 3, what Noah was saying is that you can see they're both to the x power. That is one way of thinking about it, because then you could go ahead and pull that out. I'm guessing it's the way that you went right now.
I mean, I put that on the top, but that doesn't matter.
So then what does that show us?
E is a constant, so bottom ones.
So then 0 to the infinity is
0.
for sure?
Yes.
Not indeterminate?
0. Well, technically, it's like the bottom one, anyway, so it's 0.
How's the bottom one anyway?
Because it's approaching infinity.
Or then
I think it's 0 to the infinity. Someone go to L'Hopital's. It was really recently. It was section 9.2, right? Is 0 to the infinity and indeterminate?
Yes.
No. What?
No,
isn't it 0?
no, here, no, it's section 9.2.
The fact that we're unsure.
Oh wait, no, isn't it 0 to?
It's what?
the question?
0 to the infinity.
No.
Infinity to the 0.
So infinity to the 0 is
That's not
indeterminate.
cap.
1 to the infinity is indeterminate. So 0 to the infinity is not indeterminate?
The infinity to the infinity is determinate.
Is determinate?
Indeterminate.
No,
Pause. Infinity over infinity, we all know is a determinant. 1 to the infinity is indeterminate, and infinity to the 0 is indeterminate. I was making sure that you guys weren't just going the easy route and making an answer without understanding that you could make that answer.
Thank you.
0 to the infinity is determinate. We can say that it does approach, yes, indeed, 0. The bottom does right. Okay. With that, if you want to think about another way you could think about if the bases are stronger, then as you're raising them both to the exact same powers, a higher number raised to a higher number raised to the same power as a lower number will always win. So yes, the bottom wins, yes, the limit is 0. Could you do L'Hopital's? That'd be a mess. Because you would have to make it ln on both sides and bring down the x. It would be possible, but be disgusting. So it is nice that we know that 0 to the infinity we can say is indeed 0, which means that
And it's 3, 1, 2 at the moment.
right now, because my top was e to the x, it's growing slower than ln of x, so I can say that 3 is greater than 1, and so therefore I also know 3 is greater than 2. So technically I have an order right now, 3 and then 1 and then 2, and I still need to deal with number 4, with this guy.
3 to 4.
Well, I said I had to deal with number 4, but yes, we do need to figure out who we want to compare. So we can either deal with, or we could compare our smallest one, 2, with 4, hoping that 4 is going to be lower than him, and then we'll be done. We could compare this guy with our fastest one so far to see if he'll be faster, and then we'd be done. Or he could end up somewhere in the middle, and we have to compare him with the others just to be able to figure out where he goes. So do you guys think with x to the x, or what did you do? Did you think he was faster, or did you think he was slower? It looks pretty fast to me. E to the x is a constant, right? And that's a variable too. So if we think he's faster, we should compare him to the fastest one, which would be number 3. So we go ahead and do the limit as x goes to infinity of x to the x all over ln of x to the x.
It's the same thing.
It's the same thing, huh? Oh, it's the one above, yeah. So we can go ahead and take out the x. We could do L'Hopital's to show why this is going to end up being infinity, why x ends up being stronger, because we have the infinity over infinity, which would be 1 over x, which would be x, which would then be infinity. Long story short, we do get infinity to the infinity, which is not indeterminate because ever bigger, and x is approaching positive infinity, so ever bigger positive numbers being raised to ever increasing positive numbers is going to be what?
Positive.
Ever increasing, yeah, so infinity. So who wins? Number 4. So therefore, hopefully in order from slowest to fastest growing would be 2, and then 1, and then 3, and then 4. You guys agree?
Yes.
Anyway, I thought that was kind of an interesting exercise. Number 43 was a question that we had. Let me go ahead and...
Misty, which do you want each of these to be?
What?
What do you want each of these to be worth?
Out of 10. No, when you're done with that, just the filing, and then I'm good. Okay, number 43, Corey, that was you. What was the question, bud?
Just at 4.
What?
Number 43, that was your question. What was the problem?
It's fine.
As you're looking it up, let's go ahead and peek at Alan's number 6 really fast. That was another question I got brought up. We're gonna go back to that. On this one, really quickly, we were comparing Alan of x with the square root of x because they both seem to be behaving similarly if you just think about the graphs and not thinking about the graphs on top of each other. So then mathematically, we compare the two by putting one over the other, and you could have done it in either order unless they established one. Jason, Trish. And as we're looking at it, guys, let's respect a classmate that has a question. As we're looking at it, if I just think about plugging in infinity, and Brendan asked this question, by plugging in infinity, I'm able to think about the basic graph, and so I'm just thinking, oh, okay, as x goes to infinity, ln goes up, very slowly. As x goes to infinity, square root goes up, still seemingly very slowly. But I can still say infinity over infinity, which leads me to being able to think about L'Hopital's. And so then the derivative of ln being, the derivative 1 over x being, then we're able to, I would have thought about it as 1 over x times the reciprocal of 2 square root x over 1, which does end up simplifying down to kind of similar to, I forget whose question it was, but with the powers, 2x to the 1/2 over x to the 1. I can subtract the 2 powers and then end up with x to the negative 1/2. At which point I can see the bottom wins, the degree on the bottom is lower. So therefore the limit must be 0. And remember, if the limit is 0, that means that the numerator is moving slower or has a slower rate of growth than the denominator. Does that make sense? Cool. Number 43 is where we're going next. No, go ahead.
Couldn't you also think about the simplified x as rewriting the 1/2 on top of the negative x and negative 1/2 to the bottom and just adding?
Oh, the negative 1/2 flips it up.
Yeah.
Yeah, that works good. I think I've been doing too many complex fractions and pre-cal kids, and so it's naturally where my head is going, dividing is multiplied by the reciprocal, etc. You're right. That does make a little more sense. Number 43. Corey, did you find it?
Yeah.
Okay, what's going on, bud?
You have to find which of the algorithms is the most efficient, and it's n log base 2 of n.
Let's see if I have it.
It's in the notes.
Oh, I do have this. Okay.
That one.
We didn't do it, so let's go and look at it.
Yay.
Thanks for finding it. I appreciate it. So we have 3 different algorithms for solving the same problem. Each algorithm provides for a number of steps that is, okay, here's the key for what you were asking, Kyle. The number of steps is symbolized by the order of these functions. So this isn't saying people's rating of the program. This isn't saying how much the programmer likes. This is exactly how many steps it's taking to accomplish the task. So of course we want the slower one, aka the smaller one, aka the fewer steps necessary. Which of the algorithms is likely the most efficient in the long run? Well, basically what we're trying to look at is if for a certain programming they need to take so many number of steps, we want to look at the most efficient will be the least, the lowest, and if you want to think about it in comparison to what else we were doing this homework, the slowest. Not the slowest in how it runs, but the lowest in how many number of steps it takes. Does that make sense for you?
Mm-hmm.
So then we're really just looking for the lowest one. Now we could look at it and say, oh, I think this one is the lowest one. Let's test them with the other 2, and if he's indeed lower, then we're good, we're done. Or we could just say, let's compare 1 to 2, 2 to 3, and then we'll know 1 to 3. Did you guys have a particular order that you chose? 1 and 3, because they both have log base 2s. That's probably what I would have done too. So then, it doesn't really matter. We're doing it as n goes to infinity, not x, because that's our variable. Looking at the 2, pretty quickly you'd be able just to simplify a log base 2n out, and an n. Because that would reduce, and as you're looking at it, you have 1 over, well, any logarithm, even though it increases slowly, what does it do to infinity? So therefore, bottom wins, this one is 0. So right away I know that, yeah, Because 3 is larger, so right away I say, well, he's not the most efficient because he takes more steps than 1. Or greater number of steps. Then I would just go ahead and compare 1 and 2. How'd you guys compare?
Make it.
Good. You can reduce the powers of n. So 1 minus 1.5. I would just have n to the 1/2 down below. L'Hopital's would probably be one of the easiest ways to go from there because you technically have infinity over infinity. But as you take the derivative, this guy will end up, just for sake of simplicity and time, being 1 over n ln of 2. This one will end up being 1 over 2 square root of n. And when you compare these two,
Oh, the square root of n is gonna cross out.
right, you're going to be able to simplify those powers. So you're going to end up with the limit, as n goes to infinity, of 2n to the 1/2 over n to the 1 ln of 2. You can reduce those powers. You end up with an n to the 1/2 in the denominator, since the variable's in the denominator. Who wins? Bottom. So therefore, since the bottom wins, I know that 1 is also weaker than 2. So what's the most efficient program? All right, cool kids. Those are the questions that I was able to figure out we had. We did not spot check section 9.2 on Friday because of Grace and because of some of the ASB, etc. people gone. So we're going to go ahead and spot check that right now. So go ahead and turn to section 9.2 so I can spot check it. I will go ahead, after you guys have seen your Forever Endeavor quizzes, I will give a +1 if you have 9.3 ready as well. Woo! If you don't have it ready, you don't lose any points.
9.2 was my best section. Look at all these corrections.
So 9.2 is what we're grading. 9.3, if you have it ready, it'll be a bonus point on your spot check. But we are in our notes. Notes open. Ooh, writing down something to do with an improper integral.
I'm sorry, I need to stop. I need to stop.
Alright, kiddos. This is too much. As I come to you, show me 9.2 first, and then show me 9.3 if you have it ready. Or just say, I don't have 9.3, so I'm not going to grade. So you're writing notes on section 9.4. Improper integrals, integrals with infinities in the bounds, and or discontinuities in the bounds. Infinities in the bounds and or discontinuities in the bounds. In the bounds or within the bounds, I should say. Discontinuities in the bounds or within the bounds. Interesting. 9.2, check. 9.3? Check. Let me see, Gabby, what do you got?
This is 9.2.
Good.
I thought it was separated too.
I did 2.5. This is half bonus. 9.2, good. This is half bonus.
Yeah. Highly recommend.
Somebody appreciates
Highly recommend. Highly recommend.
Thank
I'm
you.
proud of you. See, I'm just proud. I'm just proud of people, you know?
Kiddos, I want you to draw a picture of the situation going on in the example.
Huh?
Draw a picture of what's going on. Yeah.
We're gonna both probably.
It's right
Yes, that's what that looks like.
there. And it's just-
It looks like a parabola just cut in half and then stretched. No, it is though, because the parabola is just cut in half. That's what it is with this.
It's from one to
Thank you so much. You just told me. You suck.
like this, right? It approaches zero.
Oh, yeah, one line.
Alright, Reed, you take one to a team. I was gonna look at yours. Too late.
So, read what I prescribed.
Yeah, the calculation is in my binder.
The one where all the text is out.
Yeah. Because I let one day binder for.
Alright guys, improper integral time.
We'll be for those. Sort myself. Burn myself. Sorry. Lucky 18
Alright guys, this homework won't be due until Thursday. Hey, it's not tomorrow.
Yes, thank you. Thank you, Miss
Alright, cool kids, what's the picture?
It goes like a flipper?
It's like, it's this. Shaded on the.
Okay, I was completely wrong.
If that made any sense.
Yeah, exactly. I know my graphs. I know my
I
graphs.
didn't know where it's like this.
Except LN. Oh, yes, I know where you
If there's only one, I thought there was two. Because it's one to infinity, Caroline.
Interesting. Anybody who looked at Gabriel's horn, it has something to do with
I was
that?
right.
Okay,
What's Gabriel's name?
It's the.
if you rotate 1 over x squared, or even 1 over x, either way, if you rotate it, it's the horn that's formed as you go to infinity, so it's an infinite horn. Question, how do we evaluate improper integrals
Limits.
with limits? We can't do definite integrals unless we have definite bounds, and we can't do or have definite bounds within infinity, so therefore, we're going to go ahead and establish this and say, hey, this is the same thing as the limit as b goes to infinity of 1 to b of 1 over x squared dx. Ooh, what can we do now? Okay, well, what is the integral of 1 over x squared?
Get a 1 over x.
That's not good. I like my straight line better. I like the straight line. Now what?
Plug in
So I end up with negative 1 over b
plus.
minus and negative, so plus 1. The limit as b goes to infinity. Now what?
You plug in infinity, but 1 over infinity is 0.
0 plus 1 is?
1.
Oh! The infinite area is constant?
Well, it's approaching it.
It's approaching, nice for that. But it does seem to be stabilizing, ooh, converging, ooh, stabilizing towards 1.
Explain that last part again?
Yes.
Integrating? Plug in the bounds,
Yeah.
set the limit. Bottom wins, 0, 0 plus 1 is 1.
Gotcha.
If you rotate it.
Yeah, we haven't rotated yet with pi r squared. Go ahead, Jonathan.
I'm confused on how plus one goes with that minus one.
Oh, right, never mind.
Got it. FTC minus negative. Okay, that brings us to definition of improper integrals with infinite integration limits. That's not the only possible types of improper. But with infinite limits, we can take a limit or establish the infinity as a constant and then have that constant approaching what we need it to be, which is either approaching a positive infinity or approaching a negative infinity, or maybe approaching both. So if you have an improper integral with two infinite bounds, it gets a little more complicated because you're going to have to take two different limits and split the integral up. But we're kind of used to that, like with absolute value. And the improper integral will converge, stabilize, if the limit exists. An infinite limit will diverge. Or I should say the improper integral will diverge if the limit does not exist. My spacing is a little funky, so hold on. I don't know why it's funky. It just is. I just need to separate these two, but anyway. As you guys are writing, I am going towards your, let's see, class folder. Notes. Forever Endeavors.
Number 11.
That would be number 12. I might be wrong though.
I think that's 11, because we did have number 10, unless we did have a number.
But we did the special sequences. Wasn't that number 11?
I thought that was 10.
Oh, it's number 10, but my 11th slide. I apologize.
See, I'm not sure.
Here we go. Let me go get a bit better picture because that one's very off-centered. Don't worry, it's back.
Awesome, thanks, Miss Dave.
You're welcome. Endeavor number 11.
Did you say it's a virus?
Yes.
What's a virus?
We should all do that for a day.
It is quite catching.
It's absolutely brilliant.
I was watching Harry Potter this weekend.
Happy Christmas, Harry.
Alright guys, we'll have fun with this more tomorrow. Come and be ready, we're diving straight in.
That's the best country. Don't French.
Yeah, let's go to France. I want to go to France and just speak really bad. No problem, I'll get it. Thank you.